So, welcome to this Java session. Okay, what we want to do is the idea of Java puzzlers is taken actually from the Java 1 conference. In those days when Sun Microsoft still existed, Joshua Bloch and Neil Gefter, two guys working at Sun Microsystems at the time, had a regular session at the Java 1 conference in San Francisco called Java Puzzlers. And what they did was they presented a couple of lines of code, of Java code of course, and then the audience was invited to guess what it does. So it was doing some puzzling, surprising stuff. And I'm stealing the idea here. So the idea here is I will show you a couple of lines of code of Java source code using Java 8 streams and lambdas. Who has never used the Java 8 streams? Anybody? Good. So I assume that you know at least something about it. And I will give you some examples, and then you can vote whether you can figure out what it does or whether you just don't know what it does. Okay, so my background, as she already said, I'm doing training for a living, training C++ and Java training mainly. I've been publishing a couple of things. I'm writing a column for a German magazine. German is my native language. And I've been authoring the Java generics, frequently asked questions, if you ever looked it up. So that was me, basically. So then also I look into all the new language features, and if something is new, like Java 8 coming with new language features and a major extension of the collection API, then I look into it and prepare it. Okay, so the first puzzler, we will talk about forEach and what forEach does. What I'm using here is the IntelliJ IDE. You see the top part is the puzzler in question, and the middle part around here, can you see this? I'm just commenting in and out, so it's a split screen, yeah? I'm commenting in and out the various puzzlers. Down there, we see what it produces. So let's look into the source code here. What I'm doing is pretty simple. This is my stream source. It's a source, an array of strings containing the characters from A, B, C to H, I think. It's cut off there. So we have 8 characters in there. And I take this stream, take this underlying stream source, this character array, turn it into a stream, and then I do a forEach. Okay, so the output, let's run it again. The output is as to be expected. In order, we have output the characters that are contained in the underlying array. Now, what happens if I go parallel? Question is, will we see the same output? The idea of streams in general is you use parallel streams in order to achieve better performance, but otherwise you want to have the same behavior, just faster. So will we see the same output if we run this stream in parallel? Who says, yes, we will see the same output? Different output? Ah, that's good. Don't know? It depends. Oh yeah, that's good. That's a good one. What does it depend on? Ah, okay. So you see here, we will see different output. And this question here, well, it depends, is not entirely wrong. Because if you look into this, why does it produce different output? It depends on the underlying implementation of forEach on a parallel stream. That's exactly what we want to look into. Let me see. Can I get it back? Yep. So why does forEach on a parallel stream produce garbled output? That's basically what the Java doc says. With these stream operations, it really pays to take a look into the Java doc. It has a lot of explanations. And among other things, it says, well, the behavior of this operation is explicitly non-deterministic. So you can get output in any order. Yeah? The idea is we have ordered input, we have A, B, C, D, and so on and so forth. So we have a certain encounter order in the input stream, and we will not have any preserving of this encounter order if we run it on a parallel stream, so non-deterministic behavior. This is because of the way in which the underlying stream actually works. If we work on a parallel stream, what the forEach does is it splits the task of printing all the characters from the underlying source into subtasks. So it splits the underlying stream source into halves, into quarters, into eighths. It depends on the length of the underlying stream source and also on the number of cores. And so in my case, I'm saying I'll split it into quarters. I mean, the split is actually deeper. It is 4 times the number of cores you have available on your machine. So on my machine, I would have 16 subtasks because I have 4 cores. But I mean, it wouldn't fit onto the screen. So we have subtasks there. This is the fork phase, splitting up the underlying stream source, and then we have an execution phase. And in the execution phase, we have number of core, many threads working on these subtasks that we've created by splitting the underlying stream source. And then, as you can imagine, what are we doing in the execution phase? We are printing the characters from each of the segments. And so we have several 4 threads working in parallel, all of them printing at the same time. Of course, we get garbled output because they all print to the same output stream. So if we had only one core, one underlying core, we might see ordered output, even on a parallel stream, because nothing works in parallel then. So in that sense, it depends. But if you have more than one core, you will see garbled output most likely. Okay, next example. So I give you the next puzzler. Let me see. Puzzle number 2. I'm using the same underlying stream source, our characters, from A to H. And we will run with this sequentially. This time I'm not doing a forEach as the terminal operation. Instead, I'm doing a reduce, and my reduce just concatenates the strings, the characters, from the underlying stream source and prints the resulting concatenated string. So if we run this sequentially, we will see the characters in order, as is to be expected. Now, if I run this in parallel, will we see garbled output again? Or will we see something else? So, who votes for garbled output like with forEach? Something else? Ordered output. Okay. Doesn't know? Some people are not sure about it. Okay, so let's see what it does. Are we going parallel? Yes. Okay. Same output. Let's try it again. Yeah, it produces consistently the same output. So here we get the same behavior. Regardless of whether our stream is sequential or parallel, we get the same ordered output. So this is a order preserving, and basically it's a property of the reduce function. So if you look into the Java doc of reduce, reduce is described as performing equivalent to a sequential execution. It doesn't say it is actually done sequentially, but it guarantees that the result is as if executed sequentially. It works in parallel, but the result is an ordered result, different from what forEach produces. Okay. This is only true if, the Java doc also provides information regarding requirements that are imposed on the arguments that you pass to the stream operation. And we passed 2 arguments. We passed an identity value, an initial value, and we also provided a function, an accumulation function, the string concatenation in my example. And there are requirements to both of these parameters that we pass, and if we violate these requirements, if we do not meet them, then the result might be different. We will explore this in a minute. So what is expected of the initial value is that it must be the identity regarding the accumulation function, which means if I apply the accumulation function to the identity and something else, the result must be something else. So basically the identity is the neutral value regarding the accumulation function. And the accumulation function itself must be an associative function. So it can't be anything, it must meet certain requirements. So we did it all right in our example. See, if I do string concatenation, then the neutral value, the identity regarding string concatenation, is an empty string. Empty string plus something else yields something else. So we met the first requirement, we used an identity, and also we used an associative function. Just a little bit of algebra here. Commutative is not required. Commutative is asking for more. Commutative means if you apply the accumulation operation to A and B and A, the result must be the same. This is not required. This is why I used the example of string concatenation, because string concatenation isn't commutative. If you say hello plus world and world plus hello, that obviously yields different results. But it is associative. It is associative because, the matter in the way in which you place the parentheses doesn't matter. So if you have 3 values being accumulated, it must not make a difference in which order you accumulate them, whether you accumulate the first two first or the second two first. And you see, if you have 1 plus 3, 1 plus 2 plus 3, three different strings, it really doesn't make a difference with the string concatenation. Okay, not associative operations are obviously not acceptable here as accumulation functions. So if you, for instance, would be using integer minus or something like this, it doesn't meet the requirements. Okay, so what happens if we violate these requirements, if we just ignore them by chance or, yeah, just deliberately? So let's explore this. What happens? Next puzzler. Okay, you can take a look at it. You see, I'm using a different initial value. In this case, I'm not using an empty string. I'm using some kind of prefix. Okay. So if we run this sequentially, we would certainly see the prefix followed by ABC and so on and so forth. What happens if we run this in parallel? Will we see the same result as under sequential execution, or will we see something different? So who votes for the same result? Okay, we are good. Something else? Doesn't know? Some people abstained. Okay, let's see. No, I should run it first. Sorry. Let's see what happens. Yeah, that looks pretty regular. Yeah, it looks like it inserts the initial value before each of the characters, which is a little misleading. This happens because our stream source is so incredibly small. If we use a larger stream source, like the entire alphabet, let's see what happens in that case. Whether we still get my prefix followed by a character or something else. So we have a parallel stream. This time the stream source includes the entire alphabet. We still use a non-identity value as the initial value, and we run it in parallel. And this time it looks a little more garbled. You see, I see the presumed identity value, my prefix value, and a couple of characters, 1 character or 2 characters. It's irregular in this case. Why does this happen? Now, if you think of what happens if you do a parallel reduction, what it does is similar to what we're doing for each. We have the fork phase. We split the underlying stream source into halves, quarters, eighths, and so on and so forth. In each of the subtasks now, each of the worker threads that are running in parallel and are doing the execution phase in parallel takes the initial value, my prefix value, and then concatenates all the characters or the strings from its segment. Yeah? So each of them takes the same initial value, so they all take my arrow symbol, and then they attach the characters that belong to the segment that the respective thread is responsible for. So clearly my prefix value, my initial value, will appear a couple of times. In the join phase, so each of these tasks produces a sub-result, my arrow symbol followed by some of the characters from one of these segments. And in the join phase, all these sub-results are concatenated to the overall result, which gives us the entire string in which the initial value appears several times. And now it is again platform dependent. It depends on the size of the underlying stream source and the number of cores that I have, basically the depth of the split that will be applied, what the actual result will be. It is ordered in the sense that all the characters still appear in the right order, but we do not know, we cannot predict how many of my arrow symbols we will see in the overall result. So it's an unpredictable behavior. And this is usually a bad idea. The idea of streams is you should use the streams in a way that sequential execution yields the same result as parallel execution, unless you can live with unordered results like with forEach, where you really do not care in which order the stuff is printed by forEach. But otherwise, it should exhibit the same behavior, or at least a predictable behavior. Okay. So let's try the second requirement. The accumulation function must be associative. I was trying to find some kind of function that doesn't meet the requirements, and what we came up with is we will toggle the first string and then concatenate the second one. And toggling just means we turn uppercase letters into lowercase letters and vice versa. And this is a non-associative functionality. See, if I take three characters, A, B, C, and I put the parentheses around the 2 first, the overall result is a capital letter B and small letter C. And if I put the parentheses in a different way, I get a different result. So this is an example of a non-associative accumulation function. So let's see what that does. Let me see. Okay. So you see, we have the same underlying stream source, the small character source in this case, and now we are using this non-associative accumulation function, but I'm again using the correct initial value. Okay, let me see. Now we have this here. I think it's this one. Okay. So I'm running this sequentially first. You see here, I have a sequential stream, and I'm running it in parallel afterwards. Will we see the same results, or will we see different results? So same result, okay. Different result, don't know, not sure. A couple of people. Okay, so let's see. Yeah. It's not the same result. Yeah? So we get different result. If we apply it sequentially, you see a regular mix of capital letter and small letter. Yeah? We have a capital letter followed by a small letter. If we reduce this in parallel and use the non-associative function, we get some kind of mix. Yeah? One capital, 2 small letters, 1 capital, 1 small letter, so it is irregular. And it is again platform dependent and non-deterministic what the exact result will be. It's different from what we get sequentially, and it's unpredictable because it depends on the platform. So let's see where this is. So in this case, the associative function, or let's say the unpredictable behavior, stems from the join phase in that case. What happens in the execution phase is each of the threads takes the initial value, the empty string, and then applies the accumulation function. So we have a predictable result because each of these subtasks is executed sequentially by each of the threads. So we get a predictable result for each of these subtasks. But what is unpredictable is how do we associate the sub-results that appear in the middle, somewhere here in the middle. If we have, it depends on the depth of the split, whether characters that appear in the middle of the source will be prepended to the second half, or will be the suffix to the first half of the results. So, and it depends whether they are prepended or suffixes to something makes a difference regarding how often characters in the middle are toggled. So again, it depends on how deep the split is, what the actual result of parallel execution with a non-associative accumulation function will be. So again, this gives me a different result depending on the split. So sequential execution, you see how the parentheses are placed, gives me the regular result of 1 capital, 1 small letter. If I have a split into halves, yeah, I get this result. If it's a split into quarters, I get this result, and so on and so forth. Different results depending on the underlying platform. Okay, so violating any of the requirements. This is just an example. Reduce has some requirements regarding its arguments. Pretty much all the stream operations have a certain amount of requirements that they ask for regarding what you provide to the stream operation. So in this case, if you violate the requirements, what you will see is predictable behavior with sequential streams, but unpredictable behavior with parallel streams. Which is a hint that you should, if you use streams, you should always test with parallel streams, because if you make any mistakes and violate the requirements, you would not even notice if you just test with a sequential stream. Most of the bugs become visible as soon as you go parallel. And the idea is that perhaps nowadays you do not have idle cores, so you know that you are using sequential streams for the time being, but 5 years from now or 10 years from now, somebody might want to just switch to parallel stream, and if you haven't tested with parallel, you can't do this without risking bugs and unexpected behavior. Okay, something else. So far we've been using an array as the underlying stream source. And an array is pretty predictable. We have an encounter order. We know what the first, the second, and the last element is. And now we want to use an entirely different type of stream. Streams can be generated. So there is a static operation named generate in the stream interface. And generate generates a stream, an infinite stream with as many elements as you like. What you have to supply to the generate function is a so-called supplier. A supplier is a functionality that doesn't take anything but returns something. It supplies something. Basically, the supplier produces the next element for the created stream. So the supplier is called over and over again. Each time the next element from the underlying stream source is needed, the supplier is called and produces the next element. Okay, let's see how this behaves. This is my generate function here. You see, I'm trying to generate numbers. I am using an atomic integer initialized to 1. And then, well, you probably can't really read this. I am calling generate, and in generate, I provide a supplier that increments the atomic integer each time it is called. So it's creating the atomic integer 1, 2, 3, and so on and so forth. Okay, this can go on forever. If I just say generate and then do some kind of terminal operation, it will run forever because this is an infinite stream. I limit it to 16 elements. So I say generate the stream and then limit it to 16. And then I want to do a reduction in the end. Yeah? And in order to be capable of doing a reduction, concatenating strings, I turn the integers into strings by calling integer toString. And then I concatenate all the string representations of the generated numbers. Okay, first let's run it sequentially. This is sequential execution. Well, not surprising, yeah? 16 numbers, the incremented atomic integers. Now what happens if I go parallel? Will we see the same sequence? Will we see something else? Will we see the same 16 numbers in different order, or will we see different numbers? So who votes for we will see the same output? Some. Will we see the same figures in different order? Will we see different numbers? Anything else? Okay, let's see. Yeah. Sort of. Different numbers. But somehow in order, yeah? They are still sorted. Let's try it again. I mean, you know, it's fun to do parallel execution a couple of times again. See different numbers, yet other ones. And let's do it yet another time. See, we get different result each time we call this. How does this happen? Okay, generate. The Java doc tells us. The Java doc says, okay, generate returns an infinite stream. It's a sequential stream, obviously. And it is an unordered stream. Unordered means the elements that we generate appear in any order. Yeah? There is no encounter order. I mean, my expectation, or perhaps the expectation I suggested, was that we get a stream that contains 1, 2, 3, and so on and so forth, like what we've been seeing with sequential execution. But this isn't guaranteed. It's what happens with sequential execution. But as soon as we turn it into a parallel stream, we have an unordered stream and elements appear in arbitrary order. That's expressly what the Java doc says. Okay, how does that happen? You have to look into the implementation in order to understand why this happens. And if you look into the implementation, you end up looking at internal abstractions like so-called splitterators. A splitterator is an extension of an iterator. An iterator knows how to visit all the elements, and a splitterator, in addition to iteration, knows how to split the underlying stream source. So the splitterator is some kind of sophisticated iterator. And every stream source has a splitterator. And for stream sources created by the generate function, they use a so-called unordered slice splitterator. That's an internal abstraction, which you will be seeing perhaps if you go and debug the stream operations. But it's entirely internal. You are not supposed to know this. And what it does is it creates so-called slices. And the slices are basically arrays, and the arrays are filled by calling the supplier again and again. And these slices are filled concurrently. So basically what they do is they create these slices, yeah, and several threads concurrently call the supplier and try to fill their slice with whatever number the supplier returns. So you will have some of the numbers ending up in the first segment, you will see some other ones in the second segment. It depends on the time execution and how fast each of these threads calls the supplier, which number ends up in which slice. Yeah, it's entirely unpredictable. It depends on the timing. Yeah? And for this reason, the underlying stream source that is created by a generate function is unordered to begin with. And now if we go parallel, what happens is, well, one of these segments will be split and executed, and you will see some part of one of these slices. That's what we're basically seeing when we print our 16 values. So we will see 16 values, they will stem from any of these slices, and you will see any figures somehow sorted, but you don't know which figures. Yeah? So what you get is an unordered stream. Also, it's interesting, I mean, what would this unordered stream source do us any good? They actually say generate is suitable for generating constant streams. Well, if all the stream elements are the same, which is meant by constant stream, so if you just generate 1, 1, 1, 1, you wouldn't see any difference. Yeah, you wouldn't see that it's unordered. Or it is for generating streams of random numbers. Yeah, it's a little more random than the random numbers in the first place, so you wouldn't notice that this is an unordered stream again. But if you really expect something that is ordered, generate is the wrong function to begin with. Okay, there is another one for generating infinite streams. It's the iterate function. Iterate also creates an infinite stream, and this time you have to provide an initial value, here called a seed, and you have to provide a unary function. A unary function is a function that takes something and returns something of the same type. And now the elements that this stream generated by iterate consists of is the seed, f of seed, f of seed, and so on and so forth. So this unary function is applied to the previous value to create the next value. Okay, this way I can keep going and create an infinite stream again. So what happens if we use iterate? Let me see. So this is my example using iterate. Again, I'm trying to create the numbers from 1 to 16. And no, this is wrong. So, you see, I take the seed being 1, regular integer 1, and my unary function is I plus 1. So I increment. Yeah? And then I limit to 16. And then I do the same mapping to strings, and the reduction, the concatenation. So if we run this sequentially, we will see the expected sequence of 1 to 16, no doubt about this. What happens if we go parallel now? Will we see interesting output like with the generate function? Or will we see this output that we receive if we work with a sequential stream generated by iterate? So will we see the same output as with the sequential stream? Okay. Will we see something different? Okay, let's see. So we go parallel. Yeah. Okay, could be good luck. Let's repeat it. Now, even if we repeat it. Now we have predictable result. We get the same result under parallel execution that we get under sequential execution. That's what we want. That's a good example. And again, here if you look into the Java doc guarantees that this time we get an infinite sequential ordered stream. And the order is exactly seed, f of seed, f of seed, and so on and so forth. So this time the Java doc actually tells us, yeah, that in this case we can expect the ordered sequence 1 and so on and so forth. Okay, so this time it works as expected. If you look into the underlying stuff, this time they use a different split iterator. And the split iterator they use is a so-called iterator split iterator. That's the most basic one. Yeah? It creates not slices but batches again are arrays. And this time what they do is they make sure that each of these arrays is filled by just one thread at a time. So there's one thread filling the first segment and another thread filling the second segment, so that we really see the result of iteration in order appearing in these different batches. Okay, and then it is guaranteed that we see the first batch in the output being concatenated to produce the output stream. Okay, what we've been discussing here is basically which operations are order preserving. And order preservation means that the input stream has an encounter order to begin with. Encounter order is the notion of that there is a first element, a second one, and so on and so forth, and a last one. So if you have a stream source that is ordered, and you have a terminal operation that is also order preserving, you will see the encounter order of the input stream somehow reflected in the output stream. Yeah? So forEach was an example of an unordered terminal operation, and we got a garbled output. That is to be expected. That's a property of forEach. But we've seen that reduce is an ordered terminal operation. So if the input sequence has an encounter order, we will see the encounter order in the result of reduction. If the underlying stream source doesn't have an encounter order to begin with, like with the one we generated using the generate function, then you can't expect any ordered output, of course. And among the regular arrays, for instance, have an encounter order. All of the collections except hash set have an encounter order. Hash set doesn't have an encounter order because it could be rehashed. And after a rehash, the elements would be delivered in a different order. That's a property of hash set. It doesn't have an encounter order being guaranteed. And regarding the terminal operations, collect is one of the frequently used terminal operations. With collect, it depends on the collector, whether it is order preserving or not. The collectors that you supply to the collect function, they have so-called characteristics. And if the characteristics have unordered and concurrent set, then you will get unordered results. Yeah? And so, for instance, the collectors that you most frequently use, probably like to list, to set, to collection, this is an ordered collector. And if you do something like a to concurrent map, so if you have a collector that collects into a concurrent collection, then you will have this unordered flag being set for that collector, and you get garbled results, like with forEach. And there's also forEachOrdered, which is different from forEach, order preserving. Okay, let's look into map. Map is just an example of an intermediate operation. And the question is, what is the effect of intermediate operations on the order of the overall result? So what I'm doing here is I use my input stream, and then I map each of the input strings by using this toggle function. So I would turn my small letters into capital letters, and then I would perform the concatenation. If I do this sequentially, we will see the toggled results in order, no surprise here. If we do this in parallel, will it do anything different? Will we see the same result? Something else? Okay, let's try it. Same result. Yeah. The point is, intermediate operations have no effect whatsoever on the encounter order or the preservation of the encounter order. It all depends on the terminal operation, the property of the terminal operation. The only intermediate operation that creates an encounter order is sorted. After sorting a stream, it has an encounter order, namely the sorting order. But intermediate operations never destroy any encounter order. So let's talk about sorted. So I'm using the previous example here, where we generated the underlying stream source and learned that the result of the generated stream is an unordered stream source. And now I'm trying to fix it. Yeah, so generate creates an unordered stream, and then I sort it. After sorting, it should have an encounter order. And then I limit it to 16 and do my mapping and the reduction. And now I'm hoping that I will see an ordered result, because I sorted it. Will I see an ordered result? I mean, the numbers from 1 to 16, that's what I want to see under parallel execution. So, after sorting, will we see an ordered output? Will we see unordered output? Will we see something else? Okay. Well, let's see. It takes a while. Yeah. So what happened? The result is an out-of-memory error. So it's neither ordered nor unordered, we get out-of-memory error. Why does that happen? Okay. There's hardly any hint in the Java doc this time. The only thing that the Java doc is saying is, well, sorted is a stateful intermediate operation. And stateful is trying to tell you something. Stateful means a stream operation is stateful if it somehow has to keep state and modify state while you are iterating and operating on the underlying stream source. And sorted actually has, they talk of so-called barriers that are introduced. And sorted introduces two barriers. So if you have a sequence of stateless operations on a parallel stream, all these stateless operations are really executed in parallel, and then the result of these stateless operations, like a filter or mapping, for instance, it goes into a barrier. The barrier basically is an array. So the result of the first intermediate operations goes into an array, then sorted takes that array, sorts it using a parallel array sort, and the result of sorting goes into yet another array. And on that second array, the remaining operations are performed. Now you can imagine if I have a barrier, an array, and I fill in elements from an infinite stream, the barrier grows and grows and grows infinitely until we run out of memory. So stateful operations, they are telling you two things. First, you must expect that there might be barriers. They might be filling up data structures. So sorted on an infinite stream is a bad idea. It's asking for trouble. It's asking for out of memory, basically. And even if you use it on a limited stream, not an infinite but a finite stream, sorted will also, because of the state that it accesses, will be fairly slow when you execute it on a parallel stream. Because if you have this intermediate barriers here, imagine you must fill them with several streams, and you must read it with several streams, and you need coordination. So there's a lot of overhead for doing a parallel sort. So worst case, parallel sort is slower than a sort on a sequential stream. So stateful is telling you don't use it with infinite streams if you can help it, and also don't expect miracles if you use it on parallel streams. It might not even be faster. Okay. Parallel sequential. We've been using parallel a couple of times, but there's also a sequential function. Have you ever used the sequential function? Okay. So I have my example here. That's the example that we used before using a mapping. And I toggle it. And you see I do it on a parallel stream. And if I have forEach as the terminal operation, we see garbled result, as is to be expected. We see the toggling, and afterwards we do this forEach. forEach isn't order preserving, so we get the garbled output. Now I try to fix this. My idea of fixing this is, well, I want to do the mapping in parallel, but the forEach I want to do sequentially. in order to maintain my encounter order. So this is 7a. Will it work? I mean, will I get an ordered result? If I say, okay, do the mapping in parallel, that's fine. That doesn't destroy the order. And then do a sequential for each, so that I have an ordered output. Will we see our ordered output? Will we see garbled output? Don't know? Many people don't know. Okay, good. Let's see, do we have us here? Yeah, we see ordered results. What we don't see is whether mapping was executed sequentially or not. My hope was that the mapping is done in parallel to speed it up, and that only the for each is running sequentially, and we can't see this. Yeah? So I modified the example slightly. You see I'm blowing up the mapping function, and I do some output. I'm printing the thread, the worker thread, the name of the worker thread, that does the mapping. Otherwise it's the same. I do parallel, I do the mapping, this time with the print out of the thread name, and then I do it sequential and for each. Okay, and if we let this run, what we will see is, okay, let me switch back. We will see, yeah, we have ordered output, but we also see the mapping is done by just one thread, namely the main thread. So it didn't run in parallel. The mapping didn't run in parallel. Everything was executed sequentially. Okay, not quite what I had expected. So why does this happen? Well, the description of sequential is kind of mysterious. The Java doc says, yeah, the stream might return itself if it was already sequential, and otherwise it changes the stream state to be parallel sequential, depending on which one I call. The point is, what happens internally is each stream has a parallel flag. And if you call parallel, you switch on the flag. If you call sequential, you take it back. So if you do parallel and sequential and parallel and sequential and parallel and sequential, you flip it back and forth. And now if you know that intermediate operations are lazy and terminal operations are eager operations, meaning that the intermediate operations do not actually do anything. The entire execution only happens as soon as the terminal operation kicks in. See, if we have an example like this, we create a stream, we do an intermediate mapping, and we do a terminal for each, then we read this sequence of stream operations kind of horizontally. Yeah? We create a stream, then we do a mapping, which gives us an output stream, and then we stuff the output stream into the for each, which prints everything. What actually happens is vertical execution. As soon as the for each starts, mapping doesn't do anything. Mapping just creates some internal data structures, but it does not yet visit any of the elements of the underlying stream source. Only when for each starts. For each takes the splitterator, the iterator basically, takes the first element and then performs the entire sequence of map and for each, and takes the next element and does map and for each. So we have vertical execution, pipelined execution. And now with that in mind, yeah, if you now look into my example, where I'm saying, oh, I create the stream, and then I switch on the parallel flag, and then I say mapping, and mapping doesn't do anything yet. It just creates some internal data structures, and then I say sequential and take back the parallel flag, and then for each starts. And for each, and actually the setting of this parallel flag at the point in time when the terminal operation kicks in, that's the only thing that counts. Yeah, so if I flip it back and forth, the only thing that has an effect on the overall execution of the pipeline is the setting of the flag as soon as we enter the terminal operation. So basically I can say parallel and sequential as often as I like. The only thing that counts is the setting at the point in time when we hit the terminal operation. So everything is done sequentially here, even the mapping, as we've seen. Okay. So also you see a difference here between stream operations on the one hand and other methods that are basically maintenance methods. Stream operations are defined in the stream interface, and functions like parallel and sequential that just change some configuration details of the stream itself, they are defined in a class that is called base stream. Yeah, it's a super type of all the stream interfaces. Okay, do we still have time? We still have a couple of minutes. Then let's take a last look at forEachOrdered. I mentioned it in passing that there is a order preserving version of forEach. That's the last thing we look into. Okay, this is the example. I'm again doing my mapping. I'm doing it on a parallel stream now. And I'm now hoping that I get ordered output despite of using a parallel stream, because I'm now using forEachOrdered. The regular forEach would give me garbled output. forEachOrdered will hopefully give me ordered output. So we are using a parallel stream. Will we see ordered output when we call forEachOrdered? Yes, hopefully we will. Any opposition? Yeah, okay. Let's see. So we have a parallel stream, we do parallel mapping, and a parallel forEachOrdered. Yeah, we get an ordered result. Yeah, we see ABC, the toggle stuff in order. And this time we see, yeah, it's working in parallel. We have several threads, the main thread and a worker thread being involved. 2 of them only, okay. Actually, there should be 4, but I mean, see the time that it takes to speed up the threads. So we have 2 of them working here, but we have multi-threaded execution here. So eventually we have parallel mapping, and using forEachOrdered we still have ordered output. And this is what actually forEachOrdered says, yeah? It works with several threads and it preserves the encounter order if provided the input stream has an encounter order. What it does not say is that forEachOrdered is typically slower than forEach. There is additional effort for maintaining the encounter order. And what they do is they do the splitting, as they usually do. In the execution phase, remember with the regular forEach, we would in the execution phase do the print line, the printing, so that we get the garbled output, because all the printing to system out is done in parallel. With a forEachOrdered, the only thing they do in the execution phase is the intermediate operations. The terminal operation, the actual forEach, is deferred to the join phase. And in order to do an ordered output, what they build up during the execution phase, or in preparation for the join phase, is a so-called completion map. So they build up a data structure that tells, or that contains information for the join phase, so that they know, okay, we do all the intermediate stuff in parallel in the execution phase, and in the join phase, we first have to do the forEach on the first quarter, and then on the second quarter, and then on the third quarter, and so on and so forth. So they actually build up an extra data structure, and they have to navigate that extra data structure in order to preserve the order. That's the overhead that forEachOrdered creates compared to forEach. So it's measurably slower, actually. Okay, so what you've seen is a little exercise on preservation of encounter order if the underlying stream source has an encounter order, and the terminal operation is order preserving. We see the encounter order being reflected in the result. And sorted is the only intermediate operation that creates sorting order. All the other intermediate operations have no effect. Regarding ordered streams, we've seen arrays, collections, all collections except hash set, and the result of iterate is ordered. Examples of unordered streams are hash set and what generate produces. And the ordered terminal operations are reduce, forEach, and collect, provided you use an ordered collector, like toCollection, toSet, to list, for instance. And unordered terminal operations are forEach, collect with toConcurrent map, or any other collector that has the unordered flag characteristic set. Okay, do we have questions? No remaining question? Okay, you can ask me later on. Then thank you for your attention.